Okay, thank you very much. So I share my screen, and I hope everything works. Okay. So you see everything, I hope?
Yes.
Yeah, let me thank you again, Monica, and of course, Sylvia and Giovanni for the introduction to be able to speak here and to present this result, which is in fact joint work with Riccardo Molle and Matteo Rizzi and Gian Maria Verzini. Since I don't know the audience, so I decided to give first an introduction to this problem of normalized solutions, because it presents some features which are not present in the problem when you kind of the more standard approach when you look for semilinear elliptic equations using variational methods. So the motivation is when you look at nonlinear Schrödinger equations, like the one I wrote here in a standard form, and you make a standing wave ansatz, so psi of xt is e to the I lambda t u of x, then of course you are led to a semilinear equation for u, where also lambda appears. So in principle, in this ansatz, lambda and u are unknown. So equations of this type have been investigated since ages, but actually in most papers, lambda is described. But when you look at the time evolution of the Schrödinger equation, then the L2 norm is conserved. So the L2 norm of psi squared over n, this is independent of time. And so it makes as well sense to describe the integral of u2 of u squared, that is the L2 norm or the mass of u. And so this is the topic. So I look at this semilinear equation with prescribed mass. Integral u squared will be prescribed. Then lambda cannot be prescribed, but will appear, in fact, as a Lagrange multiplier. So to get a feeling for this type of problem, let's look at this standard focusing nonlinear Schrödinger equations, where you know more or less, not really everything, but we know quite a lot. In particular, we know that this problem has a unique positive solution, radial, and so unique up to translations, of course. So then let's look for the mass constraint. In fact, the problem for fixed lambda, u sub lambda, the solution for fixed lambda, can be obtained from the solution for lambda equals 1 by a simple scaling in this way. And then, of course, we can see how the L2 norm of u sub lambda depends. It just is the same as the L2 norm of u1 up to a factor involving lambda. So now we are interested in which values the L2 norm of u sub lambda can achieve. And you see if lambda can vary from 0 to infinity, is positive, but can vary from 0 to infinity, it depends on whether the exponent here is 0 or not 0. So if in the critical case, when the exponent is 0, this corresponds precisely to the case p equals 2 plus 4 over n. And this plays a special role in this normalized solution problems. So as you can, or maybe let's just go back. You see, if p is not different from 2 plus 4 over n, then varying lambda, we can achieve all values of for the L2 norm of u sub lambda. So for this solution of this problem, where lambda is still varying, but the L2 norm can achieve each value. So this is what I just wrote here. So if p is different from 2 plus 4 over n, then you can prescribe a. This has a solution, u sub lambda comma lambda. The lambda depends on this value a, and this solution is unique up to translations. However, if p is equal to 2 plus 4 over n, then the only value a for which this has a solution is this value when a is the norm, L2 norm of u, and capital U is the problem for lambda equals 1. But in this case, the solution is not unique up to translations. There exists family, a one-parameter family of solutions, namely this family u sub lambda lambda. These u sub lambda all have the same L2 norm. So this 2 plus 4 over n is the mass critical exponent. And it also plays, in fact, a role for the time-dependent nonlinear Schrödinger equation, namely if p is mass subcritical, so it's less than 2 plus 4 over n, then this solution of this time-dependent nonlinear Schrödinger equation exists for all initial values psi 0 in H1 of Rn, and the solution stays bounded. If p is equal to 2 plus 4 over n, global existence of solutions depends on psi 0, And so it exists if psi 0 is bounded in the L2 norm. It's small in the L2 norm, but then we may have blow up. And if P is larger than the mass critical exponent, then you have global existence if the H1 norm of the initial condition is small, and in general you have blow up. Okay, so now let's come to our semi-linearity problem. So this is the problem 1 to 2, so the equation together with the L2 norm. This is what we want to solve. So solutions can be obtained as critical points of the energy, written here, J of U. So just you see the grad U square term, the V of XU square term, and the potential, which come here for the primitive for little g is capital G. But you don't see the term integral lambda U squared. This lambda term appears as a Lagrange multiplier. So because we look at this functional constraint to the sphere in H1, where the L2 norm is equal to A. So we can solve our problem by finding critical points of J constraint to the sphere S sub A. And lambda then is just a Lagrange multiplier. Again, let's investigate what's happened to get a feeling what happens for the standard nonlinear Schrödinger equation when you just have a homogeneous nonlinearity u to the power p. Then when you take the Gallardo-Nirenberg inequality, so then this gives you a bound for the LP norm of u in terms of the L2 norm of the gradient to some power gamma and the L2 norm of u. The L2 norm of u now is prescribed in our setting. This is just the number A. Gamma is explicitly given by this number n times 1 over 2 minus 1 over p. When you plug this inequality into the definition of J, you get a lower bound for J. And here you see that you have the integral of grad U squared appears with the power or with the exponent gamma p over 2. And then clearly if gamma p over 2 is less than 1, this functional is bounded below and coercive on the sphere. And then you can investigate what does it mean gamma p over 2 is less than 1 with the explicit value of gamma. And you will not be surprised that this is equivalent to that p is mass subcritical. So p is less than 2 plus 4 over n. J is also bounded from below and coercive on S sub A if this coefficient is less than 1/2. And this is the case if, for instance, p is equal to 2 plus 4 over n and A is small. If p is equal to 2 plus 4 over n, then this coefficient, this exponent here is equal to 1, but we can make this coefficient less than 1/2 and again get J being bounded below and coercive. Now, last slide with the mass subcritical case. So for a general G, for instance, take a G here in this model nonlinearity where the exponents P sub J are all smaller than 2 plus 4 over n. Then you can solve this problem by minimizing J on S sub A. So you try to solve this minimizing problem. But this is not really trivial. The work started in the 1980s by Pierre-Louis Lyons and Charles Stewart. But even recently, in last year, there is a nice paper by Ikoma and Miyamoto, who considered a kind of general type of nonlinearities G, but let's say with this type of model. So it's growing mass subcritical, but being independent of X. And they found conditions on V of X converging towards 0 as X in the norm converges towards infinity, so that this infimum is achieved. So this is really a non-trivial problem, even in the kind of let's say take this kind of class of nonlinearities to find conditions on V so that the infimum is achieved. Okay, so in this talk, I will deal with the mass supercritical case. So it is our old problem, but the model nonlinearity is now, say, a sum of homogeneous nonlinearity with different exponents, but all being bigger than 2 plus 4 over n and being Sobolev subcritical, so less than 2 star. Okay, so then the first result, now quite old result in this direction, is due to Jean, which is by now quite really well known. This problem has a radial solution for every positive value A of the L2 norm. And Jean gave a certain conditions on G so that this theorem holds. I will not state these conditions here. And quite some time later, we took the same set of conditions of Jean and proved that there exists, in fact, an unbounded sequence of radial solutions for every positive value A. This is some joint work with Sébastien de Valériola. And so these kind of results and methods have been extended to much more general situations. Right now, I listed a few topics here, quasi-linear Schrödinger, also systems have been investigated, and so on. So since I need a little bit the method of proof, because we need parts of it for the case when we add a potential here, we will be mainly interested in the potential V of xu. Then let me recall briefly the basic idea of the proof of this result of Jean. So you look at the functional, J of u equals integral grad u squared minus integral capital G of u, capital G, the primitive of little g. You constrain it to the L2 sphere and fix for positive rho a subsphere of the L2 sphere, namely you fix the L2 norm of the gradient. So this B sub rho separates the sphere SA into two components. One where the L2 norm of the gradient is less than rho and one where it is bigger than rho. And this can be used to prove a mountain path structure, which has been discovered by Jean in his paper. Namely, there exist U1 and U2 in the sphere, which are lying the two different components separated by the L2 norm of the gradient being equal to rho sub 1. So that J of U1 and J of U2 is less than the infimum of J on this separating sphere or this mountain path range. So this is a typical mountain path structure now on the sphere, so we get a Palais-Mail sequence. But the problem which appears now for the in the normalized solution problem is that it is not so clear how to prove that this Palais-Mail sequence is bounded. In particular, we cannot use this expression J prime of UN applied to UN, that this is O of 1 times norm of UN. This is not true, because J prime of UN is only small if I constrain it to the tangent sphere of the sphere, to the tangent space of the sphere at UN, but UN is orthogonal to the tangent space of the sphere. So this we cannot do computations with this. So this identity does not hold. And then one can prove the existence of a bounded Palais-Mail sequence by a trick, which is already Tanaka has mentioned in his talk on Monday in a much more general setting. So you scale u, you look at h star u being defined via this expression e to the n over 2 times h times u of e to the hx. Then this h star u has actually the same L2 norm of u, so it defines a continuous path on the L2 sphere. If u has L2 norm a, then h star u also has L2 norm equals to a. Then you look at j of h star u, you can get rid of the h in the argument of u, and then you simply get this functional, which is also now differentiable with respect to h. And then we think of this as an extended functional depending on h in R and u in the L2 in S sub a. Then you see if h is equal to 0, then u is equal to 0 star h. So we get the mountain path structure for j gives a mountain path structure for j tilde, namely j tilde evaluated at 0 u1 and 0 u2 is less than the infimum of j tilde when you take over all pairs hu such that h star u lies in this b rho 1. So this is the old mountain path structure for j, and it extends to a mountain path structure for j tilde. So then we get a Palais-Mail sequence for j tilde, now consisting of pairs h and un. Being a Palais-Mail sequence means that the gradient of j tilde with respect to u and with respect to h converge towards 0 as n towards infinity. Now, this gradient u term is just the gradient of J at Hn star Un. So this converges towards 0. So we get a Palais-Mills sequence for J on the sphere. Okay, that's not yet an improvement. But now this condition here yields the following. It means that the following integral P of Hn star Un converges towards 0. P of U is defined as here. And so this P of Hn star Un converging towards 0 means that Hn star Un can be used to show that Hn star Un is a bounded Palais-Mills sequence for J restricted to the sphere. So P of U equal to 0 is just the Poisson identity, which is satisfied by any solution of our elliptic equation, semilinear elliptic equation. And so it makes sense to try to find a Palais-Mills sequence where the Poisson identity is almost satisfied. And this Hn star Un is, if you attended the talk by Tanaka on Monday, is a PSP sequence in the sense of this series of papers by Cingolani, Hirata, Ikoma, and Tanaka. But they, in the talk by Tanaka, there was a much more general setting. But this, I guess, was the first example or main example for this approach, which I learned from the paper of Jean-Jean, but it seems that Tanaka had an even earlier results in that direction. Okay, now for our Palais-Mills sequence, we get also a sequence of Lagrange multipliers. And so this equation minus Laplacian Vn plus lambda n Vn equals G of Vn holds up to O of 1. So now V sub n is bounded. We see, then it converges weakly. However, the weak limit has then L2 norm less or equal to A. So this is another difficulty which is not present when you have a Palais-Mills sequence for a functional defined on the full Hilbert or Banach space. And here it is just defined on the sphere. The next step is to prove that lambda n actually does converge towards lambda, a lambda subsequence, a positive lambda, and then it is not so difficult actually to show that this Vn also strongly converges. This in fact uses that the space of radial H1 function on Rn embeds compactly into the LP of Rn for P strictly between 2 and 2 star. And this is a critical point of Laplace of minus Laplacian U plus lambda U equals G of U of our problem, and it has the correct L2 norm. Okay, and for the infinitely many solutions, there's a version of a fountain theorem for functionals defined on spheres, which I proved in this paper with De Vallariola, and we have a simpler proof in a more recent paper with Yan Yu and Xiaoli Liu, where we were looking at a Shokar equation. And to get this infinitely many solutions and also this one solution, you can also apply this approach of Cingolani and Tanaka, which Tanaka has presented on Monday. Okay, now another variation which I would like to mention is that you can take the Poisson identity as an additional constraint. So you look at all U in the sphere, where the L2 norm is equal to A, just the radial functions, where P of U is equal to 0. The problem is that this is not a smooth manifold in general, but one can still have min-max values. First of all, the infimum, because J is bounded from below and coercive on this subset. And here we have a min-max value described using the genus, because J is an even functional in our setting. These are critical values of the constraint functional. I developed this together with Suave in some recent papers. So now let's come to the problem with the potential. So here I stay just with the simple homogeneous nonlinearity, but we have a potential V. We still look for solutions with prescribed L2 norm. And the result with Riccardo Molle and Matteo Rizzi and Gian Maria Vezzini, just appeared this year, is the following. So we have a mass supercritical exponent P, but Sobolev subcritical. V is in L infinity. It is non-negative. It vanishes at infinity. So V of x converges towards 0 as the norm of x towards infinity. And we also need that this map W being V of x times norm of x is also in L infinity. And then the result is there exists a solution of the problem 4, provided either the L infinity norms of V and of W are small, or let's say not too large, or the L2 norm is not too large, depending, you see, the constants depending on N and P and on A or on V respectively. So we have in fact explicit definitions for the C sub I. So this is not obtained via a singular limit type argument. And we can also deal with potentials which have singularities. However, some more remarks. We don't know of any potential V, or which is not zero or not constant, such that this has a solution for all A. So if you have some V, so we give conditions on V, and then we get solutions, let's say, for some value on A, if A is small enough. So, but we have no example of any non-trivial V such that this has a solution for all positive values of A. We also don't know about multiple solutions or sign-changing solutions. And in fact, we have problems to replace the homogeneous nonlinearity by a more general nonlinearity, as in the paper of Jean-Jean. Okay, now let me give you an idea, a sketch proof in the remaining 10 or 15 minutes for this result. So now here's our functional. It is just, you see here just the V of x times u squared term. And now we have a problem at an associated functional at infinity, namely when corresponding to the case that V is equal to 0, because V vanishes at infinity. Now this is just the functional for the classical nonlinear Schrödinger equations, which we know quite well. Then first of all, since V is greater or equal to 0, we see that J is always greater or equal to J infinity. J infinity, of course, is invariant under translations. So J infinity of u is always less or equal to J of u, and you can translate it with any y. However, y in Rn. However, if you let y go towards infinity, then this converges towards J infinity of u, because then u has, let's say, shifts, let's say the mass of u shifts to infinity, and v vanishes at infinity. So we have these inequalities. Then this implies that this J has the same mountain path structure as J infinity, and it also has the same mountain path value. You see the blue inequalities here are the mountain path structure for the function at infinity. You recall these two elements on the L2 sphere on S sub A, separated by the L2 norm of the gradient. And J infinity of u1 and J infinity of u2 is less than the infimum of J infinity on this mountain range. But you see this, if I replace J infinity by J, then I make this larger. So the right-hand side can be made larger. And the left-hand side, now I replace u1 and u2 by shifting u1 and u2. And if I let y let go towards infinity in the norm, then J of u1 shifted or translated by y converges towards J infinity of u1. So in the end, if y is large enough, then these two values are less than the infimum of J on the mountain range, satisfying u1 and u2. u1 and u2 with the shift, of course, have the same L2 norm of the gradient. So we have the same mountain path structure. However, you see, I obtained this by shifting to infinity, and in fact, the mountain path value is not achieved. So we need a different linking. So let me describe the linking. For this, we take the solution of our problem. So it has the capital U has the right L2 norm, some lambda, which is just determined by this A. There's a unique lambda. And so we have a unique positive radial solution. This is our U. And now we look at this cylinder in Rn times R. So it's the cylinder of radius R around 0 in Rn times the interval minus RR in R. And we look at a very special type of maps from this cylinder to this L2 sphere in H1. These are continuous maps. And the maps on the boundary, if y and h lie in the boundary of the cylinder, then this is just the solution U translated by y and scaled by h. Let me give you a short picture of this. So I make this a little bit smaller. And so the picture is as follows. So you have the cylinder in B sub R. So this is our B sub R. Here we have minus R. Here we have plus R. And we have a map from the cylinder. This is we look at maps gamma into our L2 sphere. And how are these maps defined? Let me also give you a picture. I have here is now Rn. Here I have the L2 sphere, the ball of radius R in Rn. So what I was just drawing is the ball of radius R, the boundary of its ball. And if you fix, let's say, a point y, here you have a point y comma h. I have a corresponding point y here on the boundary of B sub R, and I place here gamma of yh is this u scaled, let's say, translated to the point y, so that it is centered at y, and scaled by h. If I go to y comma r, then I have the u centered at y, but scaled by r, and r is much larger, so it is very much concentrated. If I go to y minus r, I have also the u, but then it is not concentrated at all. So that means, so for each y comma h in the boundary of our cylinder, I prescribe the map gamma. Okay, this is the map gamma, but inside, in the interior of the cylinder, gamma is open. It's just a continuous map into the L2 sphere. Okay, let's go back here. What we then do is we make an inf max over these gammas. So we take all such maps gamma from the cylinder to the sphere, take all pairs YH in the cylinder, apply gamma to it, and evaluate J on it. And this is what we claim will be our critical value. And here I just wrote, maybe I make it large again. And so here I wrote again what happens with J of gamma at the boundary of the cylinder. You see, at the boundary of the cylinder, then we here just have our U scaled and evaluated at and scaled with H. And then we apply J. So then this, if we let R go towards infinity, this means the point where this gamma of YA concentrates shifts to infinity, but then this maximum just moves, approaches the mountain pass value for the functional J infinity, or the mountain pass value also for J. So the functional is also, J is of course larger than J infinity, this maximum. And if I evaluate J infinity on the boundary, then the maximum is just precisely the mountain pass value. Because if you fix Y and let H go from minus R to plus R, this is just a mountain pass for the functional J infinity. Okay. Okay, so now I want to show you that this is a critical value. How do we do this? So the first thing what we have to do is that we need to prove that for our critical value, this inf max is bigger than the value of J evaluated on the boundary of the cylinder. Now this gamma J of the gamma of YH is independent of gamma if Y and H are in the boundary. So this converges towards this M infinity of A, towards the mountain pass value. So we want to prove this inequality. If we have this inequality, then we have a Palais-Mills sequence for J on the level C sub R of A. What we actually can prove is that we have an inf max which is slightly different. So we evaluate J on subsets D of the sphere, which are compact, connected, contain plus minus R star U. So this is the U centered at 0 and scaled by plus R and minus R, and have barycenter at U equal so barycenter is equal to 0 for all U in D, all these subsets. So the barycenter is just any map with these 4 conditions. So for reasons of time, I will not go into any details of that. So this, you can imagine that when this is proved in an indirect way, this inequality, but if you would have equality, then these you take a sequence d sub n approaching this infimum, and this would be, let's say, a mountain pass sequence for j, and in fact for j infinity, and then we use concentration compactness arguments. And at some point, if we have concentration, then this integral v u squared appears, and if this concentrates at some point, then in particular, then the concentrations happens at 0, then this integral v u squared appears in j and is bounded away from 0. So this is a technical proof and quite, let's say, a little bit lengthy. But so then we have this, we just proved this inequality. Now we want to prove this inf max is greater or equal to this. If we have proved this, then we can also prove that the inf max, our critical value, is bigger than this. Because this value, if we evaluate j on the boundary, this can be made arbitrarily close to this m infinity of a by making r large. So we just need to prove this inequality now. So we have to prove this inf max over this maps gamma is greater or equal to this inf max over subsets d subset s sub a. Now this is a degree argument. So we claim the following: for each gamma in gamma sub r, there exists a compact connected subset C sub gamma, such of B composed with gamma inverse of 0, which contains 0 plus minus R. And then if we apply gamma to it, we have such a set D. This is still compact and connected. It contains plus minus R star U, because C sub gamma contains 0 plus minus R. And the Barré center is equal to 0 for all u in D, because C is contained in beta composed with gamma inverse. And then we have this inequality here, C sub R of A is greater or equal than inf max if I evaluate gamma just at points YH in C sub gamma. Then I apply gamma to it. Then this is gamma of C sub gamma is such a D, and we have this inequality. Let me also give here you the idea for this. And let me go back to the picture. So if you apply the map gamma, the map beta, the Barré center map to S sub A, then you end up in Rn. But you see that beta composed with gamma applied to y comma h is equal to y for all y comma h in the boundary of the cylinder CR. Because on the boundary, gamma of YH is just the u centered at y and then scale to h. So if I fix a level h, and let just y be on the boundary, then I have the identity. So beta composed with gamma is a map for fixed h, maps the ball B sub r in Rn to Rn, but it is the identity on the boundary. Then it must have a 0 by degree argument. In fact, for h equal minus r, then we have precisely 1, 0. This is the 0 at if y is equal to 0. Also for we are in the boundary, if h is equal to plus r, then we have y is equal to 0. But for every h, we must have also a 0 in here. But degree argument actually tells you that there must exist a connected component containing the 0 for h equal minus r and containing the 0 for h equal to r. So this is just some connected set. This would be the set C sub gamma, which is contained in beta composed with gamma inverse of 0. Okay, so this is and that then gamma of C sub gamma is a subset of the sphere consisting only of elements which have Barré center equal to 0. Okay, then let's go back to the full screen. Okay, so I see time is running out. The remainder of the talk, we can go fast through the remaining step. By step 1, we have a Pallice-Mail sequence for J at this level. And this level is bigger than the mountain pass level at infinity. For this, we don't need any arguments or bounds on V or whatever. But if the L infinity bounds on V and on this map W, v of x times norm x from the theorem, if these hold, then this value c sub r is also less than two times the mountain pass value of the functional. And this is now important to prove the existence of a bounded Palliss-Mail sequence u sub n with corresponding Lagrange multipliers, and then show that lambda n converges along a subsequence and u sub n converges strongly. In this proof, in fact, already in the step 1 and step 3, we use that also this extended functional, so j tilde of hv is equal to j of h star v. Now you see this ugly term here appears, which we have to control. We need a splitting lemma for Palliss-Mail sequences. And we also use that this problem has a unique positive radial solution. And this is the reason why we cannot replace the homogeneous nonlinearity by a more general nonlinearity. So I see that time is over, so I stop here and thank you very much for your attention.